A warm welcome to everybody to our fourth session of the webinar in Glass with Rose. The talk of today is titled Direct Coupling of Fiber to Glass Photonic Chips by Laser Welding. First, I would like to show the potential of the laser welding process for the development of direct glass-to-glass connections. This approach avoids the use of adhesive in the optical path of two elements. Using this amazing technology, stable and low loss connections between optical fibers and micro-optics can be created. But it can also be extended to photonic integrated circuits called PICs. In this respect, I will mention some interesting examples to illustrate both cases. In fact, laser welding relies on an automated process that offers reliability and scalability for fiber-coupled PIC devices. Few results will be presented to demonstrate that laser welding can be implemented on PICs with the help of an automated machine. Integrate photonics in combination with micro-optics and optic components like laser and detectors are typically employed for telecom and datacom applications where miniaturization is essential to provide compact and low-power modules and high volume, like transceivers. Here, single-mode fibers are basic elements to interconnect those transceivers. However, permanent and reliable fiber coupling strategies are still necessary. Our motivation is to demonstrate that the laser welding technology can provide key features for the mentioned application, like direct fiber attachment of glass-based photonic chips and micro-optics where the optical path is free of adhesive, allowing a higher reliable connection and very dense fiber pitch using an active alignment method. The proposed process can be fully automated, allowing cost effectiveness. There is also strong interest in using PICs for special applications where additional requirements make the task of fiber coupling more challenging. For example, biophotonics, high power and quantum communication and cooling atmosphere had the common point that adhesive is not possible to be used in the optical interface, and this is mainly related to the optical degradation issue. Here we see that laser welding could also play a very important role. The work principle of the welding process is based on the absorption of the laser irradiation and a wavelength of 10.6 microns on the surface of the glass material. This effect causes local heating with a penetration into the glass from 10 to 50 microns, which can reach the desired melting point. For this approach, CO2 lasers are the best candidates because they provide stable beam quality, broad power range, small beam spot, fast processing, broad regulation of laser power, and low cost in comparison to other lasers. With the described principle, a concept for vertical fiber welding to macro-optical elements with low temperature transition coefficients is proposed. Two laser beams are laterally focused on the fused zone by employing optical elements like lenses. Focus height, incident beam angle, and laser beam diameter have to be adjusted according to the material properties of the two optical elements and the resulting working point. In addition, the time of the laser power during the welding process has to be optimized. The concept was implemented in a first version semi-automatic laboratory station where the welding process starts with the positioning of the cleaned joint areas and is completed by the melting point under defined pressure. The proof of concept of the laser welding station was firstly done for individual single-mode and multi-mode fibers attached to thin and thick glass pieces. the process was optimized in the way that we coupled light to the fiber and detect the corresponding beam profile using a CCD camera. The camera was placed under the glass piece. Here we found a good self-standing upon the fibers, acceptable homogeneity of diffusion zone, and position tolerance of around 2 microns after welding. The next step is to increase the number of fibers attached on thin glass in 1D and 2D configuration. The first fabricated sample has 4 single-mode fibers with 250 microns pitch. Some issues related to fiber positioning were detected due to tolerance of the acrylate coating of the fibers. This was prevented by removing a few centimeters of coating in the end of the fiber. Light was then coupled through each fiber core. By inspecting the underside of the glass, some artifacts were defined due to some dust particles on the glass surface. However, a good cleaning process of the glass before welding could solve it. A second sample was fabricated with A fibers into the configuration. In this case, the sample was embedded with epoxy to increase the mechanical stability of the fibers and to perform full test. The sample, which is even smaller than the empty ferrule, showed good stability when a maximum pull force of 100 millipascal was applied. Now that the welding process for 1D and 2D configuration has been tested with simple glass pieces, I would like to refer to the first example. That is a fiber copper to glass microlens array for the development of robust collimated beam connectors. The geometry of a plane convex lens was initially simulated by using CMATs, where a collimated beam can be obtained, showing an optical coupling efficient of 80%. An array of 12 microlenses was externally fabricated in thin glass where multimode fibers were aligned and welded to a single lens. A total of 12 fibers were attached, embedded, and packed in order to create the first version of a functional connector. Furthermore, 2D configuration and the use of other type of glasses with low TG values were explored as well. The second example is the connection of fibers to gradient index lenses and spacers to realize low loss free space fiber couplers. The integration of a spacer or cordless fiber between the fiber and the green lens can help to reduce the undesired return losses that are important, for example, in high power applications. Playing with the material, refractive index, and length of the cordless fiber, the return loss can be drastically reduced down to 60 decibels. The connection consists of splicing the cordless fiber and the standard single-mode fiber, and then to weld the hybrid fiber to the green lens. A glass packet of the welded collimator was proposed and tested using an optical backscatter reflectometer. A value of 54 decibels was found and compared with that obtained using a commercial AR-coated collimator. Here we can say that the results are satisfactory as the welded collimator can additionally offer a permanent and low-cost connection. The third example is based on optical exchanged glass waveguides made in panel level for the realization of electro-optical circuit boards for datacom applications, but also they can be used for emerging applications like quantum technologies. In this case, the welding process is very similar to the one used for the previous examples. That is fine alignment, physical contact, laser radiation, and embedding. Except that the fiber is partially bonded to the substrate. The reason is related to the location of the waveguides, which is very close to the surface. Despite this small difficulty, a series of 6 single-mode fibers were attached to the 6 inputs of the single-mode waveguides. The best insertion loss value was found to be 0.1 decibels and a wavelength of 1550 nanometer. Recently, a packet module that includes 2 coupled fibers was carried out where a total insertion loss value of 6 decibels was measured. In this case, each coupled fiber has 2 decibels losses and the chip itself had 2 decibels losses. Although the construction of this model is still under optimization, we see potential in applying the laser welding process to optical waveguides. Focusing on silicon nitride waveguides that had a wider spectral transmission from visible to mid-infrared, additional requirements are necessary for the successful implementation of the laser welding process. In particular, they ask for linear alignment or rotation of polarization maintaining fibers, PM fibers, because the waveguides show a polarization dependency. Submicron alignment for a smaller waveguide size. Transmission measurements in real time to carry out the welding process. Vertical and edge coupling options. The most important item is that fused silica glass is only compatible with the fabrication process of waveguides. Here we tried to implement the current welding process, but this one was without success. The background lies in the high TG value of the fused silica, which is about 1200 degrees Celsius. Therefore, the definition of a new laser welding process for fused silica is required. In these scenarios, a preheating step should be introduced in the process to reduce the temperature difference between the fiber and the fused silica chip during welding, so that both enter into melting phase at the same time. The fusion station was then upgraded to incorporate 2 heating elements, laser and chuck, new fiber and chip holders, and also 3 additional cameras. The proof of concept of the laser welding for fused silica was done using the 2 heating elements. The results are as follows. The fiber bent out of position using the planar heating chuck while it remained stable by using a second laser beam. This test led to the fact that the laser will be used as a heat source. We continued testing the new process and found out that the fiber can be held on a fused silica damaged chip where the welded fragment after pulling is a clear evidence of the fusion zone. Now that we have defined the welding concept for fused silica, we still have to consider the other requirements of the PICs. The only solution to cover all requirements was to develop a new automated machine that can control the process with high precision and at the same time ensure a safe handling of the integrated waveguides and fibers. Thanks to the collaboration with 5 contacts through the research project BitBell, a new welding machine was produced and has the following features. Bidirectional laser welding beams and beam heater, visual searching of the chip surface and fiber, routines to find welding position and manage power, thermal process monitoring using a camera system working from room temperature up to 1300 degrees Celsius, and of course submicron alignment capability. The first step was carried out by employing a PM fiber and a reference silicon nitride waveguide on a fused silica chip. The main steps of the automated procedure are rotation alignment of the PM fiber with tolerance of 1.5 degree, light coupling from 613 nanometer laser to the waveguide, fine alignment of the PM fiber and waveguide, preheating and welding in a few seconds. So, the first automatic routine shows that bits can be directly connected. Here we see clearly that light is transmitted through the waveguide. However, there is still work to be done in order to define an optimal process in the recent installed machine. The following slide summarizes the highlights of the session of today. We have learned from the state-of-the-art laser welding process for low TG classes that robust and reliable fiber connections can be done for different macro-optic elements. We have demonstrated a new laser welding process for fused silica glass, which is based on a preheating approach. The new process is recently available in automatic machines that offer scalable production. Here, our goal is the fully implementation of the laser welding technology for the development of next generation fiber coupled PIC modules. As a last remark, please take home the next 3 items. Laser welding can be suitable for high-dense fiber coupled micro-optics. Process assembly automation of fiber interfaces is an essential aspect of introducing PIC-based devices in the industry. Fused silica welding can easily be extended to other PIC platforms like SOI, indium phosphide, as long as there is a layer of silicon dioxide on the surface. I would like to extend a keen invitation to our future webinars. More information will be available on our website soon. Thank you very much for your attention, and now we can start with the live discussion.